One. Hello, everyone. My name is Francisco Leon Gomez, and we're group 10, and we will be presenting unmodeled dynamics. So what is unmodeled dynamics? It's essentially, so first of all, we need to know what model dynamics is, and that's models are created with a finite number of state variables. There are infinite number of systems contributors. Factors that are non-essential to the system are essentially ignored. Unmodeled dynamics is essentially those non-essential that were ignored and actually play a factor um, in the modeling, which we didn't take into account. So essentially, unmodeled dynamics is the motion of bodies under the action of force that is not observed but affects the body. Unmodeled dynamics often appears in many control systems due to the modeling errors or modeling simplifications. This makes for unreliable models that do not represent the system.
Unmodeled dynamics can have great effects on your pointing accuracy and pointing budget of a spacecraft system. Your pointing accuracy is your system's ability to precisely aim a sensor at a target. An example would be the Hubble telescope looking at a distant star. Unmodeled dynamics can cause the system to have undesirable orientations, which will have to be adjusted for by either having a gimbaled system or by making constant adjustment maneuvers with the entire spacecraft or system. Pointing budget is how far you're allowed to be off from being precisely dead on with your sensor or camera or whatever else you're pointing. The greater the effect of unmodeled dynamics on your system, the greater your pointing budget will have to be in order to compensate. The jitter introduced from unmodeled dynamics must be smaller than the pointing budget, or else the system may fail design requirements.
The action of a system can be described by the linear combination of all the modes. These modes can be sinusoidal functions of amplitude and frequencies, which eventually creates an accurate model of the behavior of the system. In real-world situations, there is an infinite number of modes in which need to be modeled, and a solution to this is to truncate these modes in order to identify the error in the model itself. The truncated terms are known as unmodeled dynamics. In order to respond to these dynamics, a controller can be utilized. A controller is used to record all of the incoming data of a system, including the modeled and unmodeled dynamics data. The PID controller is widely used in these situations, and its effectiveness is dependent on the control loop rate that it is using. Without good data, the ability to model the dynamics and tune for improved control can be unsuccessful. If the control loop rate is too fast, it will record all the noise data in the system. If it's too slow, most tuning procedures will be at risk by not being able to recognize small trends in the data. It is recommended that the use of the data be either 5 to 10 times faster than the process time constant, or 3 to 5 times faster than the process dead time. This will record data with minimal noise, but record the wanted trends in it. The process time constant is the time it takes for your controller to reach 63.2% of its total charge and what it is measuring. It is not necessary to tune your controller to the finest level of detail, but it is important to understand the overall behavior of the system.
So when it comes to control strategies and mitigation of the uncontrolled dynamics, there are two main cases being fuel sloshing and spacecraft flexibility. Fuel sloshing occurs when the liquid propellant in a fuel tank can slosh around and change the momentum of the spacecraft, which will cause unpredictable movement. This problem is often very hard to mitigate due to the complexity and unpredictability of it. The one mitigation technique for this that was found is fuel tank baffles. These are long flat metal plates that are attached to the inners of the fuel tank that can often control the fuel sloshing. And the second case would be spacecraft flexibility. This has three main ways to mitigate. The first being gain stabilization. This is a simple kind of all-encompassing solution. This is a method to keep the spacecraft bandwidth under its natural frequency in order to ensure that it keeps stable motion. This is a good solution, however, it can often limit the spacecraft performance. The second one would be phase stabilization. In this method, you can add compensators to the controls of the spacecraft that would adjust the frequency and ensure stable motion. This method often requires much more information regarding the spacecraft and the spacecraft frequency, so it can be difficult. And then the third one would be the state space representation. In this case, you can adjust the spacecraft frequency continuously based on feedback from the spacecraft controls. This method is super effective, however, it requires continuous monitoring of the spacecraft and can be much more work than the other two methods.
And so how does this relate to class? Essentially, if unmodeled dynamics is not taken into account, the system can fail. And we're talking about spacecrafts that have, like the International Space Station that houses astronauts, which can cause the astronauts to essentially die in space. So an example was that the space station, International Space Station, has two controllers that are used to stabilize. The adaptive controllers, like Eddie was mentioning before, are evaluating numbers that test the robustness essentially of the unmodeled dynamics. And once they test the robustness, essentially after a long time, they can react accordingly and then adjust the pitch, the roll and the yaw of the spacecraft. And so those are the two examples we can see here and here. And essentially over time, that negates the unmodeled dynamics. And these are things, so we're dealing with Euler angles, roll, pitch, and yaw, which we're dealing with in our class as well. And so this is just a real world scenario of what we can do in this class, essentially.
Unmodeled dynamics can be applied for fast and accurate trajectory tracking control of an autonomous surface vehicle. An autonomous surface vehicle, also known as an ASV, with complex unknowns including unmodeled dynamics, uncertainties, and unknown disturbances, can be addressed within a proposed homogeneity-based finite control, also known as an HFC framework. In the absence of external disturbances, a nominal HFC framework is established to achieve exact trajectory tracking control of an ASV, whereby global finite time stability is ensured by combining homogeneous analysis and Lyapunov's approach. Within the HFC scheme, a finite time disturbance observer, also known as an FDO, is further nested to rapidly, accurately track errors and reject complex disturbances, as shown in Figure 5, and thereby contributing to an FDO-based HFC scheme, which can realize exactness of trajectory tracking and disturbance observation. Aiming to exactly deal with complicated unknowns, including unmodeled dynamics and/or disturbances, a finite time unknown observer, also known as an FUO, is deployed as a patch for the nominal HFC framework and eventually results in an FUO-based HFC scheme, which guarantees that accurate trajectory tracking can be achieved for an ASV under harsh environments.
In summary, unmodeled dynamics are an unobservable but related forces on a spacecraft, can lead to severe issues such as fuel sloshing, poor pointing accuracy, system and or mission failure, or even risk of life. Ways to compensate for this is gain stabilization, phase stabilization, state space representation. It's very important to account for unmodeled dynamics and to have countermeasures in place for a successful and safe mission.
These are our sources, and thank you for watching our video.